To this point, we've seen that one of the really powerful things that regression can do is to make a prediction. It's nice to make predictions, but one of the other great things that you can do with regression is to quantify uncertainty around that prediction or around the regression coefficients. How confident are we when we make these different predictions? This idea of quantifying our uncertainty largely falls under the umbrella of statistical inference. In this video, I want to discuss the concept of statistical inference, which is about quantifying unknown values and quantifying the uncertainty surrounding them. The first part of statistical inference is to get some estimates and to properly interpret them. Here I give you an example of how to do that and get all your points in an exam or sound professional when you present a report. Let's say you run a regression of movie revenue on budget and you find that the expected revenue is 27 million plus 3 times the budget. You're asked to interpret the slope coefficient, so the number 3. A good answer would be, on average, an increase in budget by $1 is associated with an increase in revenue by $3, everything else being equal. Let's break down that sentence. First, you have to say, on average. That's because revenue hat is the expected revenue. The real revenue would be something different, but what we have here is what we expect it to be on average. Then we say an increase in budget, and here we have to replace budget by whatever our variable is. If the X variable instead is the number of people working on the movie, we would have to say an increase in the number of people working on the movie. Then we say by $1, and here the unit is important, also worth 1 point in the exam. If we are talking about the size of the workforce working on the movie, we would say an increase in the number of people working on the movie by 1 person instead of dollar. Then we have to say is associated with. If you replace associated by anything that implies causality, you lose all the points for the whole sentence. So make sure you say associated with. Then you say an increase or a decrease if you have a negative coefficient. Then you have to say in what, so in our case it's in the revenue, and by how much. The coefficient is 3, and the coefficient is in dollars. And then you end up the sentence saying everything else being equal, because other factors might change as you increase or decrease the budget. So we are assuming that here the other factors don't change, and only the budget is changing. Each part in bold is worth 1 point, and each part that is underlined is also worth 1 point. Remember that if you make a causal statement instead of saying associated with, you lose all the points for the whole sentence. Then you have to make sure you replace the underlined parts according to the regression you ran. So replace increase by decrease if you have a negative coefficient. Change the variable names, make sure you have the correct units, and don't forget the units, otherwise you're missing some points. And finally, put the correct coefficient. We have seen how to interpret a slope coefficient, but how to interpret an intercept coefficient. The intercept coefficient is a bit special. Remember, it is what we expect y to be when x is equal to 0. The first question we should ask is, does it make sense to have x equals 0? We should also look at, do we have any x equals 0 in our data? For instance, for the movie budget, having a budget of $0 is completely unrealistic. You cannot make a movie with no budget. It is also outside of the range of our data, since we don't have any movie with a $0 budget in the data. In that case, we should say a budget of $0 is outside the range of the data and unrealistic. So we should not extrapolate in this case. This is the interpretation of the intercept coefficient. Now, depending on the variable, you should say either it's outside the range of the data, or it's unrealistic, or both outside the range of the data and unrealistic, which is what we have in our case here. Other variables where x equals 0 makes no sense could be someone's height, nobody is 0-inch tall, or a product price. We don't sell products for free. So how to interpret the slope coefficient if x equals 0 makes sense and it is within the range of our data? For instance, here we have a representation of Okun's law in the graph on the right. It links the change in unemployment to the change in GDP. It does make sense to have no change in unemployment from one quarter to the next. We can see on the right that it does happen in our data. There are some quarters where there was no change from one quarter to the next. In this case, the estimated intercept is 0.859. It is interpretable, and we can say, on average, when there is no change in quarterly unemployment rate, so put the name of the variable here, we expect the change in GDP to be plus 0.859%. Don't forget to put the unit here. And then you conclude by saying everything else being equal, because you might have other changes affecting the GDP. Now that we know how to interpret a coefficient, let's talk about one of the foundational building blocks in statistical inference, the standard error of a coefficient. Statistical inference comes from this idea that we want to say something about a value in the population that we cannot know. That means that there is some real coefficient in the population, and we are trying to guess it with the coefficient in the sample. In our case, maybe we are trying to know the real coefficient linking movie budget to revenue. Usually, this real coefficient is denoted beta, the Greek letter. We get our sample and we run a regression and we find some coefficient for this sample that is our best guess of the real beta. And our best guess is denoted beta hat. So the hat says that we are just making a guess. It's not the real value. Since I don't know the true value for beta for movies, I've instead simulated some data with two variables x and y, and they could be anything. Since I simulated the data, I know what the real value for beta is. I've set it to 1.008. Then I simulated 1,000 observations using this real coefficient, and I took 3 different samples of 100 observations from it. You see that for each sample, if you run a regression, you get a different estimate for beta. We call it beta hat for sample 1, beta hat for sample 2, and beta hat for sample 3. For sample 1, beta hat is 0.97, for sample 2 it's 1.037, and for sample 3 it's 1.05. So beta hat changes with every single sample, and never it is equal to the actual population value of 1.008. So the question becomes, if our parameter estimates change from sample to sample, and we only have access to one sample, how certain are we that our estimate reflects that relationship in the overall population? Can we have an idea of how far we are likely to be? Well, that's where the standard error of the regression coefficient comes in. The standard error of the regression coefficient is the inferred, that means estimated, standard error of the sampling distribution for the parameter estimate beta hat. So if you look down at the probability density function that we have at the bottom, this is how our estimate beta hat is distributed when we draw various samples. On average, the beta hat will be equal to the real value beta. Now, this is on average, and in practice we are always a bit off, but we never know by how much. To quantify how far we generally are from the real beta, there is a standard deviation denoted here, sigma beta. Unfortunately, we don't know what it is either. We can, however, guess it, and that's what the standard error is. It is our best guess of the standard deviation of beta hat across samples. In other words, it is an estimate of how far from the real beta we could be when estimating it from one sample. Why is it important? Well, if our standard error is very small, let's say 0.01, we could be pretty confident that our best guess beta hat is close to the real beta, even if we don't know where it really is. However, if our standard error is large, let's say 10, then we know that our estimate could be either close or very far from the real beta, and our predictions could be way off as a result. It makes a big difference to say our best guess is $3 or to say our best guess is $3, but it could be anywhere between -7 and +13. As a manager, I would take very different actions based on those two pieces of information. The standard error of the regression coefficient is going to allow us to quantify that uncertainty. Smaller values for the standard error for the regression coefficient mean that we would expect the estimate to be closer to the population value, and so the predictions to be also more accurate. In simple linear regressions, there are two main things that can affect the standard error of the regression coefficient. First, the correlation between x and y. If the points are tightly packed around a straight line, our estimates and our predictions are going to be better. We also say that there is less noise in the data. As a result, this will be represented by a lower standard error. The sample size will also affect the standard error. If we have a larger sample, we will have better estimates and the standard error will be smaller. This is great because if we have too much uncertainty around the coefficient, that is, we have a large standard error, we can try to draw a larger sample to reduce it. So there is something we can do about reducing the standard error. Finally, where to find the standard error? Well, generally, any regression software will provide it automatically next to the regression coefficient. So there is nothing special to do here, just pay attention to it. In this example, we see that for the beta hat of movie budget, the standard error is 0.09. So we can guess that the real coefficient is not too far.